speaker is Gerald Schwarz from, I want to say Jerry?
Yeah, you love.
Gerald Schwarz from Bremen University. So, I want to thank Jerry again for giving me the first tenure position. And I want to point out that
No, first thing I found.
first tenure off. I actually did accept.
Yeah, but we never that.
That requires too long to explain. And beware this, there's no misprint in the title. This is an OPA principle for equivariant isomorphisms.
Thank you, Greg. And I want to thank Yvonne and Alan for organizing this wonderful conference and for the invitation to speak to you today. So, this is joint work with Penkov, who got his degree in Bochum, and Finner Laverson, somebody who works in the area of Occam manifolds. So I need to tell you a little bit about Stein, or I should say Stein, but I'll say Stein, for American spaces, and the Occam principle. So let X be a complex manifold, then X is Stein, if and only if X is bihomomorphic to a closed complex submanifold of some CN. This is a quick and dirty definition of what a Stein manifold is. So, of course, it's not a projective manifold, since you can never embed some complete manifold in CN. So it's far from being projective. And it's the holomorphic analog of a smooth complex affine variety. I mean, smooth complex affine varieties are examples of Stein manifolds. And you can also define what it means for a complex space to be Stein. Just a little more, I would have to say some technicalities, but I won't say them. I'll just say it's the analog of a complex affine variety. So it's sort of a Stein manifold when you allow singularities. I can't say it's embeddable in CN because it might have too many singularities. It's locally embeddable into CN, but then you need to say some global conditions. But just think of us, for Stein space, think of a complex affine variety. It's certainly okay. So the Occam principle has been around for a long time, and people like to sum it up in the following way. If you're on a reduced Stein space, which means there aren't any nilpotents in the structure. So on a reduced Stein space, there are only topological obstructions to solving a holomorphic problem that can be formulated in terms of cohomology. So it's a very powerful fact. It says that to do something in the holomorphic domain is only extracted by topology. That's a very powerful fact. So let me give you Broward's theorem, which is a very strong form of the Occam principle. It's really a fantastic result of Broward's from the late 60s. So you're going to let G be a complex Lie group and X a reduced Stein space. Then the theorem of Broward says the following. Well, you can consider isomorphism classes of holomorphic principal G bundles on X. Or you can consider isomorphism classes of topological principal G bundles on X. And the theorem of Broward says it's all the same. So, more precisely, I certainly have an inclusion between holomorphic principal G bundles and topological principal G bundles, just forgetting the holomorphic structure. And it says on isomorphism classes, this is an isomorphism. So in other words, every topological principal G bundle on X has a holomorphic structure. And two holomorphic structures are holomorphically isomorphic if and only if you can find actually just a topological isomorphism between the two principal bundles. So this is a really famous theorem of Broward of the late 50s, as I say. Now, why is this an open principle? Note that isomorphism classes principal G bundles are given by a certain cohomology set, H1 of X with values in G, where G is the sheaf of groups. And the sheaf of groups is just maps of open subsets of X into the group. If you take holomorphic maps of open sets of X into the group, then the H1 gives you the isomorphism classes of holomorphic principal G bundles. If you take continuous maps into the group, then that gives you the H1 then gives you topological principal G bundles. So the question of whether or not a topological G bundle has a holomorphic structure or not is really a problem about comparing two cohomology sets. So it's an example of an open principle, because all the data we're dealing with is an H1 with values in some sheaf groups. Okay, so I said it. Theorem of Broward is an open principle. Now there's also an equivariant version of the open principle due to Heinzer and Kutschebaugh. I don't want to say too much about it, but of course you can have principal bundles on X, and you can have another group acting. You can have another complex Lie group acting on the total space of the principal bundle and on the base of the principal bundle, and the mapping from the principal bundle to the base would be equivariant with respect to this group action. And they proved a version of Broward's theorem with this extra symmetry group hanging around. So there's an equivariant version of Broward's open principle due to Heinzer and Kutschebaugh, which will come in later in the talk.
When you say complex Lie group, are you excluding those named arguments?
Yes. The group that's acting is reductive. So I should have made that explicit. The equivariant version involves a reductive group. So what Kutschebaugh proposed to Thinner and myself was to find an open principle for equivariant maps. So we start out with a Stein manifold with a holomorphic action of the complex reductive Lie group G. So G is now going to be reductive. And then we have the quotient space, which I denote as X /G. This is a reduced Stein space, and I have to explain to you what the quotient is. So the space Z has points corresponding to the closed G orbits in X. A big problem when you have a group action is you have non-closed orbits, and you want to make the orbit space, you want your quotient space to be Hausdorff. And the problem is that one orbit has another orbit and its closure just louses up the Hausdorffness. So what you do in order to form a quotient is you define the quotient to be the closed orbits instead of closed orbits, so that's what Z is. And the other property that Z has is that if you pull back, if you take an open set in Z and take the inverse image of the functions on Z, you just get the G invariant holomorphic functions on this inverse image. So the structure sheaf on Z, so the sheaf of germs of holomorphic functions, pulls back to the sheaf of germs of G invariant holomorphic functions on X. And then, of course, there's a mapping, has to be a mapping from X to Z, which is more or less dual to the inclusion. I mean, HX upper z, and hx, of course, is the global holomorphic functions on x. And since I have this inclusion, this means dually and have a mapping from x to the quotient. If you want, another way of thinking of the mapping from x to the quotient is, you start with a point in x, you take its orbit, you take the closure of the orbit, and in the closure of the orbit, you find the closed orbit. And that's the point in z you map to, because z is the set of all closed orbits. I'll give you an example in a minute, which we can see things. But first, I need to introduce a slice representation. So we take a point such that the orbit is closed. Then it's a fundamental fact that the isotropy group, that's G sub x, that's the set of all elements of the group that fix x. And Gx, of course, is the orbit, so I just take x and I multiply it by all elements. I push it around by all elements in the group. So the isotropic group is reductive, and I have a natural representation of x, namely of Gx. Since Gx fixes x, it acts linearly on the tangent space, but of course it also acts on the tangent space of the, that's a typo, that's not G sub x, that's Gx. That's the tangent space of the orbit. So I have G sub x acts on the tangent space, it acts on the tangent space of the orbit, so it acts on the quotient. And this is called the slice representation of x. Another way to think of it is you can take a normal space to the tangent space to the orbit in the tangent space, and then G sub x will act on that. There's a G sub x invariant normal space, and you can think of that as also as a slice representation. And that slice representation is telling you, there's a theorem that says the action of the group in the neighborhood of this orbit is controlled by the action of G sub x on the slice representation. That's what the so-called Luna or Luna-Snow slice theorem will tell you. But I'm not going to use the slice representation right this second, but I want to define a stratification on the quotient. So, if I have a closed orbit and it has an isotropy group, let's call it H, and as you change the point that you are on the orbit, the isotropy group gets conjugated. So the only sensible thing is, to each closed orbit, I associate the conjugacy class of its isotropy groups. And I stratify the quotient by lumping together all the points which have the same isotropy group up to conjugation. So I have stratification of the quotient space by the class of the isotropy groups. That's a natural thing to do. And it turns out that the stratification is a locally finite stratification of Z by locally closed smooth subvarieties. So the quotient space Z can be pretty horribly complicated, but the strata are nice, smooth manifolds. And in fact, if you look at the closure of one stratum, if you look at the boundary of a stratum, it's a union of other strata. So it's a very nice stratification. So let me give you an example, one of the simplest in the world. So let G be just the non-zero complex numbers, the group under multiplication, and let V be C2, where T and C star acts on the points by multiplying the first entry by T and the second entry by T inverse. So let x and y be the corresponding coordinate functions. Then I want to look at the so OV means the polynomial functions on V. So this is just polynomials in x and y. And I want to find out what polynomials in x and y are left invariant under the action of this group. But of course, the only way to kill the action of the group is to multiply the guy who's being multiplied by t times the guy who's being multiplied by t inverse. So the invariant polynomial functions on V are generated by the polynomial x times y. So any invariant polynomial is just a polynomial in x times y. There's nothing else you can do to kill the action of the group. So let It's a theorem that if I pull back the holomorphic functions on C by this invariant, I'm going to get exactly the G invariant holomorphic functions on V. This is a theorem to Luna, essentially. So what I've done is I've constructed the quotient for you. This is the quotient. So I have to tell you why it has the right points, why it has the right, how it corresponds to the closed orbit. So if I have a non-zero closed orbit, make the same typo again, G times x, not G sub x. So the non-zero closed orbits, Gx, have trivial isotropy group. If I have a closed orbit, T times A and B, then, well, of course, they can't both be zero, so that means that the isotropy group is trivial. So they have a trivial isotropy group. However, there's one other closed orbit, which is namely the origin, and of course its isotropy group is G, because G fixes the origin. So the strata, so Z does correspond to the closed orbits, and the stratification of Z has two strata. One is 0, corresponding to the having G as the isotropy group, and the other stratum is C minus 0, where the corresponding isotropy groups are trivial. So that's an example of a quotient space of a representation, and here's the stratification. Generally, the quotient space is not going to be smooth. This is somewhat of an exception. But there's always a nice stratification. So let Y be another Stein G manifold with quotient mapping, which I'll call pi Y, mapping Y to Z. And I want it to have the same quotient space as X. So I want to be able to identify the two quotient spaces. So I just say they have the same quotient space, Z. And I also want another condition. I want to say that X and Y are locally isomorphic over Z if a very strong local condition holds. Namely, I have an open covering of the quotient space, so this open covering is called UI. And over each open set UI, I have an isomorphism of the inverse image of that open set. So pi x inverse UI is sitting inside X, pi y inverse UI is sitting inside Y, and I want a G biholomorphic map which induces the identity on the quotient. So that says that X and Y are just locally the same as much as you could possibly want them to be. Locally, they're the same. And the point of our work is to find an Oka principle for the situation. We want to find, it's sort of clear from the setup that the obstruction to X and Y being isomorphic should somehow be global, because there are no local obstructions. They're perfectly isomorphic locally. So the hope for Oka principle is that X and Y are G biholomorphic by a map to X to Y which induces the identity on the quotient, if and only if the topological condition is satisfied. That's what we're looking for. Now, I want to say this topologically. So, if I have an open set in the quotient, let F of U denote the G equivariant biholomorphic maps of the inverse image of U, which induce the identity on the quotient. So this is a sheet, again, a sheet from groups. So I look at, over an open set in the quotient, I look at all the G equivariant mappings, which induce the identity downstairs. So somehow in each fiber of the mapping to the quotient, I'm moving the fiber around inside itself in a G equivariant way. But that's more or less all I can do. So remember, I have my local isomorphisms, psi I. So if I look at psi I inverse composed with psi j, what is this? This is a self map of ui intersect uj, of the inverse image image of ui intersect uj into itself. So it's an element of f ui intersect uj. So I get a cocycle psi ij in, I get a cohomology class in H1 of ZF. So I have this sheaf of local isomorphisms over the quotient, and from my local isomorphisms of x and y, I get this cohomology class in H1ZF. And then it's an easy exercise to show that there's an equivariant biholomorphic map from x to y, which induces the identity on the quotient, if and only if this cohomology class is trivial, if and only if my cocycle psi ij is a coboundary. Okay, so the question of whether or not x and y are isomorphic is whether or not a certain cohomology class vanishes. But of course, this is a holomorphic question. These are holomorphic maps. So let me give you an example which is more or less Brauer's theorem regurgitated. So let's look at a special case where x and y are holomorphic principal G bundles over the Stein manifold Z. So then the quotient space is certainly the base, right? If I take the principal bundle, I divide by the group, you get the base. So the orbit space of x by G and the orbit space of y by G are all my Stein manifold Z. And x and y as Stein G manifolds are locally isomorphic over Z because the holomorphic principal G bundle is locally trivial. So they're locally the same, no problem. So x is G biholomorphic to y over Z, if and only if the two holomorphic principal bundles are isomorphic, right? If you ask, how can I find a mapping from x to y, which is G biholomorphic, well, that has to be a mapping of principal G bundles. So x is G biholomorphic to y over Z, if and only if the two holomorphic principal bundles are isomorphic. But by Brauer, this is if and only if the principal bundles are G homeomorphic. So this is if and only if x is G homeomorphic to y over Z. So I solve the holomorphic problem if and only if I can solve the homeomorphism problem. So here's an Oka principle for principal G bundles viewed as an Oka principle for maps between two Stein G manifolds. So the idea is to generalize it to a more general situation. So now I have to tell you under what conditions we can do this. So remember, I defined my stratification of the quotient Z of x and y. Well, the strata are submanifolds, and they're locally finite, and they exhaust Z, so there's got to be one stratum, there's got to be a stratum that's open. Okay, so there's an open stratum, which is always called the principal stratum. It corresponds to those closed orbits whose isotropy group is the smallest. Okay, so there's a unique open stratum called the principal stratum, and I define the principal points of x to be just the inverse image. So we say that x is generic if the principal stratum of x consists of closed orbits with trivial isotropy group, and the codimension of the remaining stuff is at least 2. So what this says is there's an open subset of x called xpr, where every orbit in there is closed, and in fact isomorphic to the group. The isotropy group is trivial. And then the only other thing I ask is that if I look at all the orbits which are not closed and isomorphic to the group, all this stuff has codimension too. So it's a pretty mild condition to Yes.
This is a very similar question, but how can you have a closed orbit with further ice?
Why not?
No,
I used an example of C star. The C star action, most of the orbits were just these hyperbolas, were just C star.
Ah, yeah, of course, sorry.
No,
Yeah, no.
okay.
I substitute compact for closed memory.
No, not compact. No, we're in the
Yes, yes.
most non-compact situation
Yes.
possible. Now, suppose I fix the simple D group H, and I look at H modules W, so finite dimensional representation spaces, with WH equals 0, otherwise my statement is stupidly false. Then at the isomorphism, only finitely many such H modules are not generic. So if you just fix your simple group like SLNC, you look at all the representations of SLNC, which don't contain the trivial one, then there are only finitely many which are not generic. So generic is really generically true. And there's a similar statement for H semi-simple. So in some sense, saying that X is generic is getting more than 99% of the cases. So the other cases are more challenging, but most cases are fine. Most G actions are generic. Okay, so now I have to get to an open principle, so I'm going to assume that X and Y are generic, and then I'm going to get an open principle for that. So let's consider a mapping now not from X to Y, but just from X to itself, which is holomorphic, equivariant, and induces the identity on the quotients. These are the kind of maps that we're considering. Then I say that psi is special if there's a holomorphic map from X to G such that psi of X is gamma X times X. So here's the simplest kind of mappings that preserve the fibers, namely the action of psi on X is the following. I take a mapping from X to G, and then I just multiply X by that element in the group. I certainly stay in the same orbit. It sends orbits to orbits and fibers to fibers. So that's a special map. And what's good about being X generic means that every holomorphic map is special. For every holomorphic psi of this kind is special. And there's another condition, of course, psi is equivariant. So psi of G times X is G of psi times X for any G in big G. So of course, since psi is equivariant, gamma has to satisfy some kind of equivariance condition. And this is the equivariance condition that gamma has to satisfy. That gamma of Gx is G gamma X G inverse. Well, how do you prove the lemma? Well, it's kind of easy because just look at XPR. Look at the points where X is a principal bundle over the quotient. Then, for the case of a principal bundle, it's clear that a holomorphic equivariant map inducing the identity on the quotient is just multiplication by an element in G. You just have to prove this lemma for a principal bundle, where it's trivial. And then, this mapping gamma extends because XPR doesn't omit any divisors. The difference between X and XPR is something of codimension 2. So if I have a mapping into G on XPR, it automatically extends to be holomorphic on the whole space. So that's the other beauty of generic X. Okay, so now we're almost in business. So let script G be the sheaf on Z corresponding to equivariant holomorphic maps gamma from the inverse. So take the U open in Z and take the inverse image and take the equivariant holomorphic maps on that inverse image to G. So this is be a sheaf on Z, the sheaf of groups, because of course I can multiply. I can multiply into groups, so this gives me a sheaf of groups. X is generic, then the lemma says that my sheaf of equivariant mappings inducing the identity on the quotient is the same as the sheaf strip G. That's what the lemma says. It says if psi equivariant inducing the identity on the quotient is of this form, is special. So the two sheets are isomorphic. And let GC be the sheaf of groups corresponding to continuous equivariant maps to G. So instead of taking holomorphic maps, which are equivariant, I take just continuous maps, which are equivariant. So the equivariant version of the Ogre principle of Heinzner and Kuchabau says that if I go from H1 of Z with coefficients in this sheaf of holomorphic maps into G, into H1 of Z with, for the sheaf of continuous maps into G, that this is an isomorphism. So it's an isomorphism of H1s. It's an Ogre principle. For these two sheets. So the corollary is that X is equivariantly isomorphic to Y over Z if and only if the topological condition is satisfied, because all I need is the vanishing of this H1 of GC where these are continuous maps. So it says if X and Y are special, then, and locally isomorphic over, X and Y are generic, and they're locally isomorphic over a common quotient, then the obstruction to them being equivariantly biholomorphic is topological. I have an Ogre principle. But it's a little hard geometrically to get your hands on what this topological condition is, so let me try to give you the topological condition in a different language. So let's see what the topological condition should be. For this, I have to talk about G-finite functions, which Wilfred talked about during this first lecture. So if I look at the holomorphic functions on X, then of course G acts on the holomorphic functions, where F goes into G dot F, where G dot F of X is F of G inverse X, for X and X. So if I have a group acting on the space, holomorphically it acts on the holomorphic function. So a holomorphic function is G finite if when I look at if I push F around by all the elements of the group, I only get a finite dimensional G module out of this. That's what it means to be G finite. And the G-finite functions, of course, are a module over the invariant functions because, of course, the group, you can't, a G-invariant function doesn't get moved at all by the action of the group. So, an HX of G module. And I can sort of name these G-finite functions by the, remember, if F is G-finite, it generates a finite dimensional G module. So let's look at fix a G module VI. Well, let VI be a finite dimensional G module, and look at the holomorphic functions which transform by that irreducible, well, usually irreducible. Look at the subspaces of G-finite functions that transform by these sub. These are usually called covariants. And then I'm going to make an assumption which is more or less locally true, which means it's not really an assumption. So locally over Z, I can do the following. I can find finitely many irreducible representations V sub I, such that the covariants corresponding to V sub I generate the algebra of G-finite functions on X, well, as a module over the invariant. Over the G invariant holomorphic function on X. And it's also true that the HI locally, you only need finitely many different kinds of G-finite functions to generate all the kinds of G-finite functions. And in fact, the G-finite functions of a certain type are really finitely generated over H except for G. So now suppose I have a mapping from X to X, which is equivariant and biholomorphic, inducing the identity on Z, and let F1 through Fn generate these spaces of covariance. Then what happens when I look at psi upper star of F? This just means F composed with Fi composed with psi. Well, by equivariance, it has to be a sum of Fj's of the same type. It has to send covariance of type Vi into covariance of type Vi. So what I get is psi upper star Fi is a sum Aij of Z times Fj, where the Aij of Z are holomorphic functions on the quotient, or if you want, they're holomorphic invariant functions elsewhere. So psi is determined by the Aij. So if I have a equivariant holomorphic map, I can determine it by a matrix of functions Aij. I have to warn you, of course, the Aij's are not unique because the Fi's may not be independent. But psi is determined by the Aij's. So that's what happens if you have a holomorphic map. So now, suppose I have phi, which is a G equivariant, just a homeomorphism. Then we say that phi is strongly continuous if phi upper star Fi is a similar sum, summation Aij Z Fj, where the Aij Z are now just assumed to be continuous. So strongly continuous means it behaves like a holomorphic map, except that the coefficients that come out are only continuous and not holomorphic. Now, a strong continuous map, so again I write this basic formula. Let me look what it does to a fiber. So the fibers of pi, well it should be pi sub x, are affine G varieties. This is a basic fact about the quotient mapping. The fibers of the quotient mapping are affine G varieties. And the covariant functions Hx, Vi generate the algebraic functions on the fiber. So therefore, phi does what? It takes the Fi's, sends them into the Fj's, multiplies them. If I'm in a fiber, just multiplies them by a constant. So phi induces a G automorphism of the fiber. So what a strongly continuous map is a continuous family of G-height isomorphisms of the fiber. It's a nice continuously varying collection of isomorphisms of the fiber. And I claim the strong continuous maps are the natural kinds of topological maps one should consider for the following reason. Suppose that my sheaf of groups F is represented by a group scheme, F tilde. So that means that I have some kind of complex analytic space F over Z, whose fibers are groups, and my sheaf on an open set U is just the sections in this group scheme. So if you're in this situation, which I must admit happens rarely, then the continuous sections of F tilde are the strongly continuous homeomorphisms. So these are exactly, if you have a space over Z which is a group scheme and gives you back script F, then the continuous sections are exactly the strongly continuous homeomorphisms. So they're the natural thing to look at. Now, of course, I just told you what a strongly continuous map of X to X is. I'm really worried about the situation of maps from X to Y. So let phi be a G homeomorphism over Z. Then phi is strongly continuous if psi I inverse composed with phi is strongly continuous. Remember, psi I is is the mapping is the local isomorphism of the inverse image of ui and x to the inverse image of ui and y. So if I take psi inverse composed with phi, that maps pi x inverse ui to pi x inverse ui. So I can say whether it's strongly continuous. And then this makes sense, it doesn't matter what psi I use. So I can talk about the notion of strongly continuous homeomorphisms, G homeomorphisms from x to y. And the main theorem is, if I have x and y which are generic and locally isomorphic, I'm always assuming they're locally isomorphic over z, then if I have a strongly continuous map between them, then there's an equivariant bihomomorphism p prime from x to y. So the theorem is, this is really the topological condition that you're looking for. So let me give you a couple of words about the proof. So I use the slice theorem again. So take a point x and x with where now I finally said it correctly, the orbit gx closed, and let wh be the slice representation. So h is the isotropic group. Then the slice theorem says the following: there's an H-saturated open set B in W. So H-saturated means it's a union of fibers of the mapping to the quotient. H acts on W, so I have a quotient of W mod H. And I can find an H-stable, in fact, H-saturated open set B contained in W, and a G isomorphism from pi x inverse U to G crossover HB, where U is the neighborhood of Z, which is the image of X. So G crossover HB is just G cross B divided by the action of H, where H acts on the right on G, of course freely it acts on the left on B, since H acts on W and B is H stable sitting inside W. So this is really an open set in G crossover HW, which is a homogeneous vector bundle for G. So the slice theorem says that locally X looks like G crossover HB. And we similarly have exactly the same description for Y, because X and Y are locally isomorphic, so they have the same slice representation, and they have the same local structure. So Y near the image of little x looks like G crossover HB, and I can use these isomorphisms to think of phi as a mapping from G crossover HB to G crossover HB. So locally I'm in this situation where I have a map between these very special G manifolds, these sort of twisted bundles. And then I do something completely simple. Remember, this G crossover HB is sitting in a vector bundle, so I have the scalar action in the second argument. So let T times the point, which is little g here and little w and w, modulo the bracket GW represents the H orbit through G comma W. So I let my T and C star act by just scalar multiplication in the second argument. So that gives me an action on G crossover HB, which is more or less, if T is small, is shrinking the fiber down towards the zero section of the bundle. And then there's a lemma, which says the following. I have my mapping, I call it phi, which should be, let phi be phi u. So define phi sub T of GW to be T inverse phi of G of TW. So I try to take the derivative in the normal direction. Then the statement is the normal derivative exists and is a special map. Namely, phi 0 of x is gamma to 1 to get a phi 0, which is is a special map, except the gamma is only continuous. So using induction and a partition of unity argument, you can show there's a homotopy starting with our original phi and ending up with a phi 0, which is special. Yeah, so that's the main technical tool in the whole proof. And now we're done. We started out with a cohomology class psi by j and h1zf. And if that vanishes, then x and y are g by holomorphic. Well, h1zf is the same as h1zg, where script g represented equivariant maps into the group. But we know by Heinzner and Kuchebaum, this is isomorphic to h1zgc, where gc represents continuous maps into the group. But the existence of phi 0, which is a special map, so the existence of phi 0 shows that this class is trivial. Okay, I can solve when I push the cohomology class over to GC, since I have a global map phi 0, which is special in the sense corresponding to GC, then that shows that this cohomology class is 0, which means that the original cohomology class was 0, which means that I have a bipolar map between the two. So that's the specific instance of the open principle using Heinzner and Kuchebaum. But the proof doesn't actually show that phi is homotopic to a G by holomorphism of x and y over z. It doesn't show that the original map is homotopic because we go through the Heinzner-Kuchebaum theorem where you lose this fact. And of course, you can ask me, what about actions that are not generic? So I'll tell you the following. There's a latest theorem, right, for which I won't give you the proof, which says if I have a strongly continuous map without any generic condition on x and y, then there's a homotopy starting with your phi and ending with a G by homomorphism x and y over z. So you have the full theorem that you could ever want. And then I have to tell you a couple words about what you can do differently. So we can't reduce to Heinzner and Kuchebaum, but what did Heinzner and Kuchebaum do? They took Cartan's proof of Brouwer's Oka principle, and they made it equivariant, and they went through the proof. So what we have to do is, we have to go through the proof and modify everything to fit our situation. Now, there's a preliminary step you have to do. I can't work with a strongly continuous map and apply the methods of Cartan. It breaks down. I have to take the phi and I have to massage it a little bit to make it better to get a situation where we can use this Cartan-Brouwer machine. So I claim that if I take a strongly continuous map, then after homotopy I can arrange the following. So let Z be in the quotient. Then there's a neighborhood of Z and a holomorphic map, a holomorphic self-map of X over UZ, which agrees with phi on the particular fiber over Z. So it says the following. Phi, strongly continuous, means I have a family of G isomorphisms of the fiber. The guy with the homotopy has the following property, that over each fiber, of course, I have a homotopy, but it says, I have a G isomorphism, but it says that G isomorphism extends to a holomorphic G isomorphism in the neighborhood. Not only that, but that if I look at psi of Z of x prime, for x prime close to x, then the whole thing is smooth. So what I do is I start with phi, and what I do is after homotopy, I can arrange that I have a two-parameter guy, psi of x and x prime, such that if x prime is equal to x, it's on my old friend phi, and if I fix x and let x prime vary, it's a holomorphic mapping. So that's the massaging you have to do. And then you can apply the Broward proof to this kind of phi, which is an extension, and you're done. But of course, there's a lot to prove in there. I mean, I'm giving you infinite detail anyway. There's even more if you do Cartan-Broward proof. So let me end by talking about the linearization problem, which is near and dear to the heart of everybody who works in transformation groups. So the question is, I have my reductive complex group G, how can it act on Cn? Or specifically, if I have an action, a holomorphic action of G on Cn, can I find a holomorphic change of coordinates such that the action of G is linear? If that's true, we say that the G action is linearizable. Okay, it's an old question. There is a nice result of Dirksen and Kuchebaugh, which says, no way. For every non-trivial group, including the monster, whatever non-trivial group you want, there is a D and a non-linearizable action of G on Cn for every n bigger than or equal to D. So as soon as n is big enough, there are non-linearizable actions of G. And what is peculiar about these, why these are non-linearizable actions, is because the quotients Cn mod G are rather horrible and couldn't possibly be the quotient of a linear action. So that's Dirksen and Kuchebaugh. Using some ideas of Asanuma, who worked in the algebraic category. But anyway, we can apply all this previous stuff I talked about to get the following theorem. Suppose that V is a G module, and that X and V are locally isomorphic over a common quotient. So, of course, the quotient is V divided by G. Then the conclusion is X is equivariant by a holomorphic to V. Notice I don't make any topological assumptions. The reason I don't need a topological assumption is, of course, that V is contractible. So that somehow obviates the need for assuming that there's some strongly continuous bound.
Would you eliminate the condition of genericity in your previous theorem?
Yeah,
That was the latest theorem.
That's the latest
theorem.
theorem.
Make sure I understand.
Yeah, the latest theorem. So I don't need. In our paper, you'll find this theorem for V generic, but in fact, we don't need it anymore.
Okay, so that's very good. Yeah.
So that X is equivariant by holomorphic to Y, to V. And of course, I don't need to assume, so of course, if I'm talking about the linearization problem, I should say, well, X is Cn, but I don't need to assume that X is Cn. That comes out in the end. All I know is that X is a Stein G manifold, which is locally isomorphic to this linear action over a common quotient. There's even a better theorem, which says the following. Suppose that V is not too small. I have to tell you what not too small means. Or maybe I won't tell you what not too small means, but again, it's a generic situation. So V is not too small, and suppose, and now I'm going to make a weaker assumption. I'm going to assume that the quotient of X by G and the quotient of Y by G are biholomorphic. I'm not assuming that X and V are locally biholomorphic over a common quotient. I'm just making an assumption about the quotient. I'm just saying the quotient of X by G and the quotient of V by G are biholomorphic by a mapping which preserves the Luna strata. I have to tell you what the Luna strata is. It's hard. But then X is G biholomorphic to V. So it's, again, a stronger theorem. It says that the Dirksen and Kuchebaugh examples work because the quotient is horrible. Because it says as soon as the quotient is biholomorphic to a quotient of a linear action, then in fact that action is linearizable, if V is not too small. So it's a stronger theorem than the one on the previous slide. So for any simple G only finitely many, V with V upper G equals 0 are too small. So this is more or less, again, not much of a condition on V. And similarly for G sets. So what is the Luna stratification of the quotient? Remember, our stratification of the quotient used the strata which correspond to isotropy, conjugacy classes of isotropy groups. But the Luna stratification pays attention to the slice representation. But the slice representation doesn't change on irreducible components of ZH. So if you take the stratification ZH and you take the irreducible components, then you lump together the components which have the same slice representation, and those are the Luna strata. So I'm assuming that the isomorphism of X mod G and V mod G preserves the Luna strata, not just the isotropy type. Just not the isotropy group stratification. So that's that, and I think that's the end of the lecture. So thank you for your attention.
Are there some questions for the speaker?
Yes.
How difficult is it to preserve this Luna stratification?
No, it's a pretty. I mean, it says locally. You see, if the two Luna strata are the same, that means upstairs there's locally a G biholomorphic map between the two. So it means preserving the Luna stratification means locally they're isomorphic. So that's something, right?
Yeah.
So that's more or less what preserving the Luna stratification means. That upstairs locally they're isomorphic, but yeah, just that.
So do you think somehow that one can make this assumption a bit weaker, or of preserving this Luna stratification?
I'm not sure what the theorem would be. I mean, in the end, of course, they're going to, if X is G biholomorphic to V, of course, it has the same everything stratification. But I don't know how to make everything we did assumes the Luna strata correspond.
Okay.
So everything we do says locally they're the same. So it's an Oka principle. You know, locally they're saying there's some global obstruction. We try to show the global obstruction damages. So it would, if we got rid of the Luna strata being isomorphic, it would be a whole different ballgame.
Yeah, I mean, I was wondering whether probably in some nice situations you can somehow skip
Yeah.
this, but it's the question of how nice the situation must be.
Yeah. I don't know if I haven't been able to think of another set of conditions which in the end would give you biholomorphic map.
Mm-hmm.